All right, ladies and gentlemen, I'm gonna write for you guys a problem where we go through and we balance out a redox reaction. And so as we're going through this video, we're actually gonna be tackling a lot of different things, a lot of different steps as it pertains to writing redox reactions. So I would encourage you, you might have to watch this video multiple times. If you need to pause it at any point, rewatch and re-listen through something, feel free to do that. But I'm about to go through an example problem with you guys where we're going to balance a redox reaction that's in acidic solution. And so I'm just going to read you the problem that we're looking at and then just kind of go from there. Okay, so the problem that we're looking at, it tells us that the reaction that we have is going to be the reaction of the nitrate ion with metallic copper, and it's going to produce nitrogen monoxide and copper 2 ion. And so our first step in balancing this redox reaction is going to be first simply identifying oxidation states. And so in order to do that, we need to write the balanced equation, or at least the equation of the reaction. And so based on what we've got, that means that we've got NO3 1 minus AQ plus copper as a metal reacts to make nitrogen monoxide gas and copper 2 plus ion. So that is our our reaction that's taking place. And so, like I said, in this video, we're going to be tackling how do we assign oxidation numbers? How do we balance or identify half reactions? And then how do we balance those half reactions to get a complete balanced redox process? So first things first, let's go through and assign oxidation states. And so for this particular substance, or this particular reaction, there are a couple things I want to just remind us of. When we have an element, elements always have an oxidation state of 0. So for our copper metal, oxidation state 0. Nice and easy. Next thing I want to take a look at for our monatomic ions. Remember, monatomic ions, like the copper 2 plus that's on the product side, they're going to take on the oxidation number or oxidation state based on the charge of the ion itself. So that's a 2 plus ion. So that means that this copper is going to have a plus 2 oxidation state. Man, so far so good. Next, let's deal with oxygen. So oxygen, we know, can be a little bit tricky sometimes, but typically it forms a -2 oxidation state, and it only changes when it's attached to fluorine or it's in a peroxide. Now, for both of these, we don't see fluorine or a peroxide, so we can give oxygen its preferred oxidation state of -2 in both of these substances. Now, that means that our nitrogen that's in nitrate has a +5 oxidation state, and then our nitrogen and nitrogen monoxide is going to have a +2 oxidation state. Okay, now when I did that, some of you may think, Mr. Kenton, I get the nitrogen on the product side has a +2. How'd you get that +5 for nitrate? So just as a reminder, remember that our oxidation states should add up to equal the charge. And so the overall charge on this molecule is 1 minus, or on this ion. Now, nitrogen was unknown, so that's an X. Oxygen's negative, so that's going to be minus. We had 3 of them, so that's -6. And it has to equal an overall charge of -1, or 1 minus. And so then it just becomes a simple algebra problem. You're going to have to add 6 to both sides, so then X equals 5. So that means our oxidation state for our nitrogen is +5. Okay. So that gives us our ability to be able to assign our oxidation states. Next thing that we're going to do, and I'm going to hope to do this on this page, is we need to figure out which substance is oxidized and which substance is reduced. Now, we can figure that out now because we have our oxidation states. And remember, oxidation is the loss of electrons, and reduction is the gain of electrons. Now, our substance that is oxidized, in this case, is going to be copper. So copper goes from having an oxidation state of 0 to +2, indicating it lost 2 electrons. So my oxidized substance is going to be the Cu solid going to Cu2 plus Aq, right? That's my oxidized portion. And then my reduction portion is going to be that nitrate ion going to nitrogen monoxide, specifically the nitrogen component. So then it goes from NO3, 1 minus Aq, to NO as a gas. Okay. And so in doing that, we have now successfully identified the unbalanced portions of our half reactions. So this step right here, the oxidation reaction is the copper to the copper 2 plus. The reduction half reaction is the nitrate ion to nitrogen monoxide, specifically the nitrogen within that. Now that we've done that, we can move into this piece about talking about how do we actually balance a redox reaction. Okay, so what I'm going to do is I'm going to walk us through how to go through the oxidation and the reduction step, but I'm going to look at it one step at a time, or one piece at a time. So we're going to start with the oxidation half reaction. So now I'm going to make the screen disappear. So if you need to, pause or copy it down as quick as you can, or pause the video, go back and look at what you need to. But so in our oxidation reaction, we have that copper as a solid got converted into Cu2 plus. Okay, and if you remember from the video I posted about how to do redox reactions, I actually included in that the kind of the steps for how to balance. And so if you need to reference that, feel free to pull that up or pull up the notes that you've taken on that so that you can use this as we're moving forward. But the first thing we have to do, just like in any balanced equation, is we got to make sure we have the same number of atoms of each element on both sides. And so for this one, actually, it's already balanced. We've got copper and copper. They're balanced. Now, if you remember the rules, it talks about the rules for balancing oxygen and hydrogens are different in redox. Now, it doesn't apply to our oxidized half reaction because we don't have any. But if we did, we would have to balance oxygen by using water, and then we would balance hydrogen by using H plus ion. Now, we can skip those steps here because that's a non-issue. We don't have any oxygens or hydrogens. Now, that brings us to our last step, and that's going to be making sure that the charge of our redox reaction is balanced. Now, currently, we've got the reaction side has a 0 charge, and the product side has a 2 plus charge. And so we recognized copper lost electrons. So we should anticipate that those electrons should show up on the product side. Now, in order to balance out this charge difference, if it's 0 on the left, that means we need to make the right 0 here. So what we're going to do is we're going to add in electrons. And so in this case, we need to add in 2 electrons to our oxidation half reaction. Now, once we do that, we've got a charge on the left of 0 and a charge on the right of 0. Now, because the charges are equal, we have now obeyed the law of conservation of charge. This is our oxidation half reaction for this particular process. Now, we're not finished. This just completes the first half of our puzzle, or of our process. So now we can go back now and deal with our reduction half reaction and follow the same steps. So I'm going to make this disappear. And now let's write out our reduction half reaction. So the reduction half reaction, if you recall, was the NO3 minus AQ going to NO gas. Okay. Now we have to follow the same steps as before. Our first step is going to be balancing out our elements other than oxygen and hydrogen. So nitrogen in this case, there's one on both sides, so I don't need to change anything. That's perfectly valid. Now next, again, following along with those rules, the next element we're going to balance is oxygen. Now oxygen, there are 3 oxygens on the reactant side and only 1 on the product side. So in order to balance that out, we balance out oxygens by introducing water molecules. So this is going to be plus 2 H2O as a liquid. Okay. Now when we do that, we've got 1 nitrogen, 3 oxygens, but now we don't have an equal number of hydrogens. We now have 4 hydrogens on the product side and none on the reactant side. So in order to balance out hydrogen, we're going to introduce H plus ions to the reactant side. Okay, so I'm actually going to rewrite it on the next line kind of directly below this. So that means we're going to have NO3 minus AQ plus 4 H plus AQ produces NO as a gas plus 2 H2O as a liquid. Okay. And so now at this point, we have the same numbers of nitrogens, oxygens, and hydrogens on both sides. So we have balanced it based on mass. But our problem is we have not balanced it based on charge. Now, in this particular process, we know that nitrogen went from having a +5 to a +2 oxidation state. So that meant that it gained 3 electrons. So in reduction, we should show that the electrons are being added to the reactant side. Now, another thing you can do to check yourself is that your reactants and products have to have the same charge, right? And so the product side has a charge of 0. Currently, the reactant side has a charge of +3. So we need to add 3 electrons there. So we can rewrite that. We're going to have NO3 minus AQ plus 4 H plus AQ plus 3 electrons produces nitrogen monoxide gas plus 2 liquid waters. Now in doing that, we've now dealt with our charge, because now the charge on the left is 4 minus 4, so that's 0. On the product side, it's also 0. So we have balanced it for charge. So this is now our reduction half reaction. Okay. So now that we've tackled both of those individually, we can now combine the two to get our final answer. So I'm going to make this screen disappear, and we're going to rewrite both of our half reactions that have been completed. So for our oxidation, that was the copper as a solid going to Cu2 plus AQ plus 2 electrons. And then it was our NO3 minus AQ plus 4H plus AQ plus 3 electrons produces NO as a gas plus 2 H2O as a liquid. Okay. Now, we've made sure that the charges in each reaction individually are equal, but now we need it for the overall process, to have an equal charge. And one thing that you're going to notice, right off the bat, is that the number of electrons that we have on the reactants and product side is going to be different, right? We've got 2 on the product side and 3 on the reactant side. And so our last step is we got to cancel out these electrons. We can't have any electrons left over. And so what we're going to need to do is we're going to need to multiply both half reactions by an integer to cancel those out. Now, between 2 and 3, that means that we need to get to 6, right? That's what they share in common. And so that means for the top reaction, we're going to multiply it by 3. And then for the reduction half reaction, I need to multiply it by 2. Now, when I do that, we would then get the following half reactions. So now we're going to have 3Cu as a solid going to 3Cu2 plus Aq plus 6 electrons. And then for our reduction half reaction, we're going to have 2NO3 minus Aq plus 8H plus Aq plus 6 electrons produces 2 NO gas plus 4 H2O, right? So now that we've multiplied by that whole number, we can then combine these two reactions by simply adding them together, right? So take the oxidation half reaction, add it to your reduction half reaction, and then you'll start canceling out and combining like terms as best you can. Now, the only terms that are going to get canceled out in this case are going to be our 6 electrons. Now, that will not always be the case. It just so happens that it works out this way for this particular reaction. Now, once we do that, we can then get to our final answer. All right, it's been a long time. We've been working through this. It kind of feels nice to finally get to the end. So, one last clean slate as we write our final answer. So, our final answer should be, we've got 3 coppers plus, we're going to have 2 nitrates plus 8 H pluses is going to produce, that's going to be 2 NO plus 3 Cu2 plus Aq plus, let's see if I can fit this in here, 4 H2O as a liquid, right? So that would be my overall balanced redox reaction. Now, even though it's our final, we still want to check to make sure, do we have the same number of atoms and are the charges the same? So with our number of atoms, we would count, we've got 3 coppers on the left, 3 coppers on the right. That's good. We got 2 nitrogens on the reactant side, 2 nitrogens on the product side. We've got 2 times 3, so that's 6 oxygens on the reactant side. Then we've got 2 times 1 is 2, and then 4 times 1 is 4, so 4 plus 2 is 6. So we have 6 oxygens on the product side as well, so far so good. We got 8 H's on the reactant side, and then 4 times 2 is 8 H's on the product side. So far, mass is conserved. So mass is conserved, right? And next we need to check the charge. So if we look at the reactant side, we've got 2 nitrates, so that's -2. And we've got 8 hydrogens, so that's +8. So 8 minus 2 equals 6 on the reactant side. And then if we go over to the product side, the only thing that has a charge is the copper ions, which we have 3 of them, which is 6. And last time I checked, 6 equals 6. That's good. So then charge is conserved. Ooh, I can't spell apparently. So charge is conserved, right? And that, ladies and gentlemen, would be our final overall balanced redox reaction for that particular process. There's a lot of steps. We unpacked and did a lot there. And remember, this was only for acidic solution. In basic solution, it's going to look a little bit different. So I'm going to be making another video here real soon so that I can show you one in basic solution. But for now, take a look at this. Try to find some example problems to work out so that you can get some additional practice with balancing it and use this as a tool. Thank you guys for stopping by, and I'll see you guys again soon.